The previous sum problem is a challenging computer programming puzzle that you'll often see on university exams or even in online courses as people learn how to code with their programming language of choice, be it Python or Java or even Mojo. The problem can be stated like this. Given an array of numbers, create a second array where each element stores a running total calculated from adding the corresponding element in the first array. It's a little easier to understand visually. I've got an array of values here, as you can see, 10, 20, 12, 28, 10, 19, 101, and 799. That would be the original set of values. The problem asks you to create a second array that stores a running total as you go through the array. So it's 10 here. Add 10, we've got 10 down here, we've got 20 here. Well, 20 plus 10 equals 30. We've got 12 here. Well, 30 plus 12 is 42. We've got 28 here, 42 plus 28. This is going towards the limit of my mathematical capabilities, but you do get the idea here. I'm not good at math, but I can write a computer program that does math for me, and that's what we need to do. Now, there are two approaches here that you can take in Java or Mojo. I'm going to show you the traditional approach. It's sort of brute force, but I'm also going to show you a second approach that uses some incubating Java APIs, takes advantage of brand new SIMD type architectures, and also follows a path that we see in artificial intelligence, machine learning, blockchain manipulation, and high performance applications. So I'm going to show you the first solution, but please stick around for this second cool solution because it behooves you to learn how people are doing modern computing today. Okay, so let's run this program. I've already got a Java application created here inside of Eclipse. I even put those numbers in here so we can kind of see what we're trying to achieve as we write this program. I've got a module info that uses incubator Java, but we don't need that right now. All I need is a Java class with a main method and I don't know what else, an array declared in here. So I'm going to say int original array equals the numbers 10, 20, 12, 28, 10, 19, 101, 799. A big jump there at the end, but we're not afraid of big jumps. So that's just the original array. Then we need the array where we've got the previous sum. So we say summed array, square brackets, equals, well, it's got to be the same size as the original array. I spelled it correctly. So that's just going to be equal to a new int array, which is the original array length. So there we go. We've now got a second array that's just got zeros in it currently, right? Which when you create a new int array of length, what was that, 8, you'll just end up with 8 zeros by default. But we'll populate that eventually. Now, as you can see down here, the first element in the original array and the first element in the summed array are always the same, right? Because that first element in the summed array is just that first element plus 0. So starting off, to make life simple, what we can do is we can simply say that the summed array first element, which is element at 0, is equal to the original array's 0th element. And that ends up putting element 0 of the summed array equal, in this case, to 10. Okay, so that's the only kind of hard coding that we'll do there. After that, we now need to do a loop that takes care of the rest. So what we'll do is we'll loop through all of the elements in the original array. So for int I equals 1, because we've already done element 0. Normally you say int I equals 0, but we've done element 0, so we can start at 1. Keep going through that original array. So original array.length. And then the standard I++ semantics here that we're all familiar with. And then inside this array, what we want to do is we want to say the summed array's value. Okay, so the summed array's value, so in this case down here it's 30, would be equal, that is calculated by taking the previous element in the summed array and adding it to the current element in the original array. Okay, so the element in the summed array comes from the previous element in the summed array plus the current element in the original array. And that's the logic. I'm repeating it there just so that I can get it straight. So the current element in the summed array, that summed array element I, is equal to, so the current element in the summed array, so say we're trying to do 30 here, it would be equal to element minus 1 in the summed array at I minus 1, plus the current element in the original array. So original array at I. Throw a semicolon on there, and I think that's all we need to do. Now you could throw some curly braces on there if you wanted to be strict with your Java. I don't mind that at all. And now we can just print this out. So system.out.println, and I can just say arrays. Oh boy, I asked my boss for arrays the other day, and he said no, use a vector instead. So arrays.toString original array. So that'll print out the original one. And now down here, we will copy and paste, because that's how I program. Arrays.toString, and then here we want the summed array. And Control-Shift-O to add in the import java.util.arrays at the top there. And now if I run this program, Java run as a Java application, boom, I end up getting the results that I was expecting. I do a bit comparison over here. Yeah, and it looks exactly like what I was predicting. So there you go. That is a nice approach to solving the previous sum array problem in Java. Now, I do have a second approach that uses Java 21 preview features, incubating APIs, vectors that access SIMD processors, and it behooves you to stick around and watch this really cool solution to the previous sum problem in Java. That's next. Now, as you may or may not know, there's a new programming language in town called Mojo, and it's positioned to revolutionize how software development happens in the AI, ML, and high-performance computing space. It's only at version 0.6 right now, but people in the community are really doing really interesting things to try and figure out how the language works and also how to learn it. And I saw an article from Maxim Zaks about how to use SIMD operations in Mojo to efficiently calculate previous sums and solve the previous sum problem. And I thought, wow, Java's got an incubating API called the Java Vector API that allows you to do SIMD-based operations. And I thought, I wonder if I could achieve the same level of performance and do what Maxim did in his article in Java. And so that's the second approach to solving this previous sum problem that I'd like to demonstrate to you right now. Now, in order to do this, you need a couple of things. You need Java 21 installed, because that's where the vector API is incubating. And you'll also need to enable the JDK incubator vector package through your module info file. So you can see I've got a module info file here that I say requires JDK incubator.vector. That'll now allow me to access these APIs. And here's how it works. So with a SIMD vector, what you can do is you can take an array of values. Say we've got 8 elements in our array that we need to do an operation on. And with a SIMD, single instruction with multiple data, a CPU can do an operation on all elements of that array at once. So rather than taking 8 clock cycles to affect 8 elements or 16 clock cycles to affect 16 elements, a SIMD operation can do it in just one. And here, let me give you an example. I'm going to create an array of shorts. I'll create a short array, and it'll just be that original array. And I'll stuff in all of those different values that we had. Now I'm using a short array because a SIMD operation is limited depending on the architecture that you're on. Sometimes it's 256 bits, sometimes it's 512 bits. So it changes from architecture to architecture, CPU to CPU. And that's a challenge for Java when Java tries to be cross-platform. That's one of the reasons why the APIs are incubating. So anyways, I've got an array here. And what I want to do is I want to create a vector that allows me to do these SIMD-based operations. So I go short vector vector equals, and then the way to create it is just to call a static method of the short vector class and say dot from array. And there's a little bit of code here. You say from the short vector preferred species preferred, we're going to pass in that original array and offset 0, so just throw the whole thing in there. This just helps to specify the size of the SIMD that we can use, and we should have enough space to operate on these 8 shorts right here. And what can you do with a vector? Well, as I said, you can take a full data set and do operations on all the data in one CPU clock cycle. So this isn't going to solve the previous sum problem, but I can say vector equals vector dot add vector. And now if I was to print out the value of the vector, you would end up seeing that all of the elements of the vector have doubled. We've gone from 10, 20, 12, 20, 40, 24, 56. So you can see all of that happened. All of those elements were manipulated in one single clock cycle, rather than having to do it in a loop that would require 8. The efficiency and the performance gains are remarkable. And this is with 8 elements. You can imagine with 16 or 32. This is the way we want to be building applications, thinking about SIMD operations. So how can we use this with our application? Well, one of the ideas was what we could do is we could actually kind of use this technology to first, do one iteration of the calculation where we use the vector to add it to itself, but the first time around we shift the vector over 1. So you can see that it's 10, 10, 20, 20, 30, like all these values are shifted over 1, and the first element is a 0. We do the add and we get a result. Then we take this result, and then we take the result and we shift it over 2, right? So you can see 10, 30, 32. Now it's 10, 30, 32 there, right? And then the next time around, we shift it over 4. So you see the result is 10, 30, 40, 70, 79, 929. You've got those numbers down here. Then you've got those numbers shifted over one more time, okay, and then added in. And then we end up getting the result, but the result is done through vector SIMD type operations. It takes a while to look at that and kind of figure out what's going on there, but the logic is solid. And essentially the shift over, you do it a number of shifts based on the log 2 of the number of elements in the array that you're using. And that also implies that the number of elements in our array will be a power of 2, just to keep things simple. But so how would we do this in our code? Well, I'm going to have to get rid of this code right here and come up with something a little bit more interesting. The way that we would do it in our code is we would say vector equals vector.add, because we're adding one vector to the other, right? Like each vector is getting added to the other. But the first time around, we're going to shift over just one element and put a 0 in where we've got the shift. So we end up saying vector equals vector.add vector.unslice 1. That's the command that's part of the, not unslickle, unslice. Unslice 1 means just shift over from the left one. Slice means shift over in Java from the right one. Okay, so that does it once. We need to do this, the square root of the number of elements in the array. Here we've got 1, 2, 3, 4, 5, 6, 7, 8. And the square root of 8 is 3, right? 2 times 2 is 4, times 2 is 8. Is that right? 3. So we need to do it 2 times. And then finally, with that vector, we will do it 4 times. Okay. Now, when we're done, we should have the result that we're expecting from the previous sum solution. So I'll print out the vector here. So I'll do system.out.println vector. And that's at the start. this now is at the finish. Click Control S after I do my copy and paste properly. It all looks good. Okay, and again, I think the results that we're going for is something that looks like this. Let's see if I can find those results up here. 10, 30, 42, 70, 80, 99, 200, 999. Let's see what we get. Run as a Java application. And boom, 10, 30, 42, 70, 80. 80 plus 19 is 99. 99 plus 101 is 200. That's what we want. 200 plus 799 is 999. And boom, all of a sudden we get the result that we want. So overall, I think that's a pretty cool approach to solving this problem in Java. Now, let me emphasize that particular solution isn't complete. We can't dynamically right now figure out how many times to do the unslice, right? We maybe should put that in a loop, and the number of slices would be based on the log2n size of the array. So, and we are also assuming that as we do that, the arrays will always be what, a power of 2, which is maybe an unfair assumption as well. But nevertheless, I think it is a super interesting application of the vector API and an interesting use of SIMD. And I would also say it's really interesting to actually take a look at how they do that in Mojo and some of the issues that arose when they tried to do the similar solution in Mojo. But there you go, a couple of really interesting approaches on how to solve that previous sum problem, the standard brute force approach, and a more modern approach that takes advantage of SIMD. Now, if you enjoyed that tutorial, why don't you head over to the serverside.com. I'm the editor-in-chief over there. We've got lots of great tutorials on Java, on the new Mojo programming language, on AI, on ML, on DevOps, Scrum, Agile, Git, all sorts of things. If you're interested in my personal antics, you can always follow me on Twitter, and I do have a newsletter where we're talking about all of the latest advances in modern programming, from what's going on in Java to what's happening with the Mojo programming language. So please check that out. And of course, if you're watching this video on YouTube, you should subscribe on YouTube.